Solids of revolution and the washer method. We are going to look at a solid formed by revolving a curve or curves around an axis. We're going to look at y equals square root of x, and we're also going to look at y equal 1/10 x, which is a line passing through the origin of slope 1/10. And we are also going to look at the vertical line x equal 4, and we're interested in the region that is enclosed by these curves. We're going to take this region and we're going to rotate it around the x-axis to form a solid of revolution. You can see what the solid is. We'll be interested in finding the volume of this solid, so we're going to be interested in taking a slice and looking at it. Here we have a disc with a hole in it. So the idea here is we can find the volumes of these solids of revolution by looking at slices, summing them up, and essentially we're going to have an integral. So let's have a closer look. First, we're going to start with something fairly simple. Y equals f of x is going to be the upper end of our region, and the x-axis is going to be the lower end, and then we're going to look between those lines. So here is our region. We're going to rotate this around the x-axis. And you can see as we start to rotate this, the solid that is being formed, and we'll be interested in finding the volume of this solid. So this is what it looks like as we've rotated all the way around. You can see our little shaded region R there, and then as it goes around the x-axis, what is swept out here is this solid of revolution. So we're going to be interested in finding the volume of this solid generated, and we're going to do that by looking at a slice. And we see that a slice here is a circle. So the area of one of these cross-sectional slices is going to be pi r squared, and we see that our r is just simply the function value or the y value. And at any given x, our radius is going to be the y value or f of x. So the area of a little cross-section is going to be pi f of x squared. Now we can take these with little thicknesses and we can sum all of these up then to find the volume. So that's where we're headed as we look at these different solids of revolution. Let's have a look if we took a function and rotated it around the x-axis then, and have a look at what we are generating here so we can get a sense seeing what we get. Now if we had this filled in here, we have this volume, and we could look at a cross section is going to be a circle, and then we take a little thickness, so we have a disc, and the radius is going to change depending on where we are, but we could sum up all of these discs then to get the volume of this solid that would be generated as we rotate this around the x-axis. So we have our pi r squared, and then we would have multiplied by the little thickness. So the disk method, if we're rotating around the x-axis, we've got a continuous function f of x greater than or equal to 0, and we're looking on the interval from a to b, and the region bounded by the graph of f, the x-axis, and the lines x equal a and x equal b is revolved around the x-axis. And so the volume of the resulting solid is going to be summing up all of these disks. The limit as n goes to infinity, so we have this definite integral from a to b pi f of x squared, that's just these circular areas multiplied by their thickness, dx. Now when you do these, you're not going to want to try and just memorize a formula and spit out a formula. You're going to want to visualize what you're doing. And so if you look at this and draw a little sketch, you go, oh, these cross-sectional areas are just circles. Well, the area of circles pi r squared, then multiplied by how thick it is, and essentially then that will lead us to the integral. We could take a function and we could rotate it around the y-axis. Typically when we do this, we would want to have x equals a function of y, and we could rotate this around the y-axis and see the solid generated. And after we get this solid, we could slice it. We're going to be slicing it horizontally here, and we could take a disk, so we have pi r squared multiplied by a little thickness. But you can see if we did this around the y-axis that our radius is going to be x, which is a function of y. So we could have here as we look at this and we try to express the area of a cross section that was made horizontally here, that would be pi g of x squared, and then multiplied by the little thickness, which would be a little delta y in the limit becoming dy. So the difference, if we're going around the y-axis versus the x-axis, is we're going to be looking at a function of y. X equals a function of y instead of y equaling a function of x. We're going to call our interval c to d. In this case, this one started, the c was 0. It could be whatever there, but they're going to be y values. And then the region that we rotate here, revolving around the y-axis, to find the volume, it's going to be the integral from c to d of pi, the radius, g of y squared, dy. So very similar, we just have x and y interchanging roles when we rotate around the other axis. Now we could have two functions. We don't have to use the axis as the lower limit or one of the limits of our region. So let's see what this would look like if we took and rotated this around the x-axis. So we're taking this region, rotating around the x-axis, and then after we get this volume, if we do a slice, we see that it is not a disk. We can look at it at various x values, but it is we call it a washer. It is a disk with a hole in the middle. And so if we wanted to compute the volume of this, it's going to be pi times the big thing squared, which would have been the disk, minus the volume for the holes, or the area for the hole, and then we'll do the little thickness. So that would be pi little r, which would be the radius of the hole squared, and we would need to take the difference of those, so we would need to subtract off for the hole in the middle. So if we looked at some region and we're not using the axis as one of the edges of the region, if we rotated this around the x-axis, you can see that right in here there's going to be a hole, and the radius of that hole is going to vary. It's going to be different here than it would be right here. So as we rotate this around and generate this solid, it will be a solid with a hole. So when we compute this, we could essentially think of finding this cross-sectional area of a disk and then find the area of the hole and subtract that off, and then we'll be able to multiply it by its little thickness. So we will call the big radius capital R, and then the little radius of the hole small r, and depending on how they were defined, which functions were which, we could use this to compute. If we look at this picture, and if this region, the upper function was f of x and the lower function was g of x, then we could take pi f of x squared, and that would be the area of the disk. The area of the hole would be pi g of x squared, and we could subtract the two. So we had pi f of x squared minus pi g of x squared. This is the hole, and this is the disk. So we take the difference there, and we have the area of that washer, and it's very common to factor the pi out in front. So if we look at this and we add our little thickness and we sum them all up, then we have the washer method. So if we have f and g continuous functions and f of x is greater than or equal to g of x, so it's letting us know which one is on top here, and then greater than or equal to 0, and we're looking on an interval from a to b. R will be the region bounded by these curves and the lines x equal a and x equal b. When this region is revolved around the x-axis, the volume of the resulting solid then would be this integral from a to b, and it is just simply the disk, which is pi f of x squared, minus the hole, which is pi g of x squared, and then we factor the pi out. And that's a good idea to do that, because then we know by properties of integrals we could actually move it right out here in front, and that will make it a little bit simpler when we find this integral. Now looking at this, basically then our cross-sectional areas are disks minus these holes in the middle, so they are washers. But what if g of x is 0? So if the lower function is 0, essentially you would be looking at the lower function to be the x-axis, and so you wouldn't be subtracting off any whole, and then you would be finding this, which is just the integral from a to b of pi f of x squared, which is the disk method. So really the disk method is the washer method with the special case of g of x being 0. Now we could revolve around the y-axis a region. We don't need to have the y-axis itself being part of the region, and then we would have our two functions. Here we have our right hand function being p of y, and then the function to the left here being q of y, and you can see as we rotate this around, imagine that's solid, and you can see that there would be, if you did horizontal cross sections, you're going to have washers again. So as we rotate, we see our outer radius is, and I'm going to draw it over here, we've got it right here, p of y. Depending on where we draw, it's going to be a function of y, and so x is a function of y here, and we could express that, and then we could subtract off this whole, which is going to be the inner radius, which is that q of y. So we can see that the disk and washer methods around the y-axis are analogous to the ones around the x-axis, but x and y interchange roles. We have p and q continuous functions with p of y greater than or equal to q of y, which is greater than or equal to 0, so p of y is going to be to the right of q of y. We're looking on the interval from c to d, and R is the region bounded by these curves, P of y, Q of y, and the lines y equals C and y equal D. And if we revolve around the x-axis, the volume of the resulting solid is going to be pi, the disk, P of y squared minus pi, the whole, Q of y squared, dy. And if we did not have the two functions, or if the q of y, the second function, was 0, then it's just simply a disk instead of a washer. Now there can be a couple other cases. We don't have to rotate them around the x or y axis. We could rotate them around some other line. We're going to look at horizontal or vertical lines. We could have a horizontal line at y equals some a value. Now picture rotating this around that axis. You can see that we would generate a solid, and when we sliced it we would still have washers, much like we did before. But we've got to be careful when we're expressing the radius here of the outside, the capital R, and of the whole, the small r, because they are not simply going to be the function values. You look here, this radius is going to be measured off from the line y equal a. So it's going to be very critical that we draw a sketch and we visualize what's going on so that we can find the radius. As we're looking here and we would see what this radius would be, it's basically just going to depend on a sketch, and there's going to be an example that will show you how to do this. Now let's just look at one last case, and that would be we could rotate around a vertical line, x equals some a value, and start to picture this, what it would look like rotated around here, and we could see that once we got this solid formed, these cross-sectionals are still going to be washers, but you've got to be careful of how you express the radius, because it's not simply going to be x is that function of y. So you would need a sketch so you could determine. So your best bet when you're doing these is to get a sketch and visualize what's going on, so you can do pi times the radius of the disk squared minus pi times the radius of the whole squared, and then we would integrate that on our interval.